All right. Hi. So some news, about the MATLAB. I asked again today in the morning, and I got no reply. So I'm sorry about that. If you want to do something about it, then put border sets for the MATLAB licenses. It's a little annoying because I already wanted to give you like a little homework so you get started with your MATLAB, but I guess we have to wait until the license is out. You can already play with it in the lab, right? You know that. Yeah, and I guess tomorrow we will do the recitation as before, some more MATLAB tricks, MATLAB programming. Right? So let me recap briefly what we did previously. So we defined the dot product and we talked about some of its properties. So let me just very briefly recapitulate what is the dot product of two vectors. Both have to be in the same dimensional vector space, Rn. So you should remember by now that their dot product denoted by this dot. Oh, I always get this wrong. So v dot w is the sum over all the coordinates multiplied together. I'm just recapitulating what we had there before. Now we know that if we do the dot product with itself and take the square root, that's called the Euclidean norm. And what is the meaning of the Euclidean norm of vector? Again, these geometric things you should remember. That's the intuition. So what is the meaning? Yeah? Yeah, the magnitude or the length, right? If I draw the vector as an arrow, this Euclidean norm, that is the square root of the dot product of the vector with itself, it gives me the length of the vector. So those are the super basic things. Then the last time we had some also basic but less trivial or less obvious things. Let me hide this window. Like this. So some less obvious properties of the dot product. So one of them was the Cauchy-Schwarz or Cauchy-Schwarz-Bunyakovsky inequality, right? So what that was saying was that the absolute value of the dot product of v times w is always less than or equal than the norm of v times the norm of w. So this was the Cauchy-Schwarz inequality. Very important inequality in mathematics. And that when I say this, then I always mean that it applies for all pairs of vectors v and w from Rn. You are familiar with this notation, like for every the quantifier thing. That's like you should have seen it by now. Okay. The other thing we discussed the last time was the triangle inequality. So the triangle inequality tells us that the norm of v plus w is less than or equal than the norm of v plus the norm of w. And again, you can have like an easy geometric intuition behind it. If you imagine that this is like a triangle, so this is, let's see. So if I have one side which is a vector v, another side which is vector w, so that would be v, w, and then the other side is just v plus w. That's how vector addition works, right? If you add the components, if you think about it, it's just like adding these two arrows together. So v plus w is this one arrow. And the triangle inequality, so this is called the triangle inequality. It tells us that this side, oh wait, maybe I should do this lock thing so it's not refocusing all the time. So that the norm of this side always has to be smaller or at best the same length as the sum of the lengths of these two other edges, right? When does it happen that this inequality is exactly equal? Yeah.
When it's a flat triangle.
Exactly, when it's like a degenerate flat triangle. When you will be doing some computations, probably not maybe already in this class, but maybe like later on, you will always want to avoid triangles that look like this, that are like almost degenerate, almost flat, because that's like an extreme, that's like a weird case, right? You can tell, and lots of computations like scientific computing break down for this case. for example, like for finite element method, we will get to that. You want some well behaved triangles, but not these degenerate cases when the angle here is almost 180 degrees. Nevertheless, these inequalities, that's something you can rely on, regardless of how the quality of your triangles or anything. That's just something that's always true. That's why it's important. That's just something you can always count on. There is one more thing I didn't mention the last time, but it's sort of interesting. There is a variation on the triangle inequality called the reverse triangle inequalities. I will just mention it here quickly. It's not super important, but it's an interesting fact that might be useful here and there. So the reverse triangle inequality. And what does it say is this. It says that the absolute value of the norm of V minus the norm of W is always less than or equal than the norm of V minus W. If you think about it, this is actually the same as saying that the norm of V minus W minus is less than or equal the norm of V minus the norm of W less than or equal V minus W. So this is, and again, of course, always, I mean for every V and W in Rn. So this is like looking at it from the other side, that instead of adding the lengths of the triangle edges, I subtract them, and I have like the other side of the inequality. Now, if you wanted to do something for homework and you're annoyed that you cannot play with MATLAB yet, then you can try to prove this reverse triangle inequality. You can go to Wikipedia and find the proof there, but that's less fun, right? You can try to do it by yourselves. And the most important thing we got to during the last lecture is the geometric interpretation of the dot product, and that is the following formula. That means that the dot product between V and W is equal to the norm of V times the norm of W times the norm of cosine theta, where the theta is the angle between the two vectors. I think there is some like better word for it. Like if I have like one vector V and one vector W, the angle, inclined angle, or how do you call it? Like the angle between two vectors. I'm blanking on some word. You know what I mean, right? If there's two vectors, there are two arrows in whatever dimension space. Like in 2D, it's the simplest thing. There is some angle, right? But in whatever dimension space, doesn't matter. There is some angle between them, and that's this angle theta. So if you want to only remember one thing from the past lecture, this is what you should remember. Because we discussed this gives you the geometric intuition, the geometric interpretation behind the dot product, right? So what immediately follows is that if the theta is greater than 90 degrees, then the cosine is negative, so the dot product is negative. If theta is 90 degrees, then the dot product is 0, and we call these two vectors, what do we call them? When they have 90 degrees angle between them. Orthogonal, exactly. We will get to it in much more detail. To orthogonal vectors, they will play a very important role. So vectors with length 1, we call unit vectors. So this is like a unit vector, just basically, I guess, recapitulating the terminology. And one more thing I should again remind you of is what was the definition of a linear combination of vectors and scalars. Linear combination. So if I take some number of vectors, let's say I take k vectors from some vector space V, could be R to n or whatever, and I take some scalars, so those are just the same number of scalars, k scalars, they are just real numbers. They can be anything, can be negative, positive, whatever. Then this thing, the sum of alpha I times vi from 1 to k is called a linear combination of these vectors. So the idea is I take a bunch of vectors, I scale each of the vectors by whatever number, and I sum them together. This is like the basic building block to get to subspaces and all these things. We will define that more formally later on. So this was just a recap. Do you have any questions on that? Anything not clear here? Everything visible? Readable? Okay. So what I want to do today is to eventually get to matrices in a constructive way, but what I will show is that matrices are basically a representation of linear transformations in vector spaces. So that's what I would like to get to, because matrices are the very basic building block, right? You know that MATLAB is a matrix laboratory, so vectors times matrices is the very basic thing in a linear algebra. So to get there, we will start with vector spaces. So I was already like sort of talking about vector spaces, right? And giving like the prototypical example of R to N being an example of vector space. And you could be like wondering, so what exactly is this vector space, right? So we are talking here like not on super precise mathematical level, but here is an example where, so I'm not showing the whole slide. Which is weird. Nicely here. Well, I can just zoom up and a little more. There you see the whole thing. Maybe I could also just do this.
Bring the screen down.
Huh?
Projecting
Oh, you think it's that? Oh yeah, all right. But this works, right? Can you read it? So let's read it all together. So what is going on here is explaining the definition of a vector space. So this sounds a little theoretical, and I promised you we are like more on the practical side of things. But the practical implication of this is that pretty much whatever we say, whatever properties, whatever theorems we prove from linear algebra, like we had some examples here, right? The Cauchy-Schwarz inequality, triangle inequality, and so on. So this all applies generally in vector spaces. One needs to be very careful because some of the properties assume Euclidean spaces. But in general, a large part of linear algebra just works generally with vector spaces. So let's take a look at what is a vector space. So it all starts in mathematics. All starts with a set, right? Set is just a collection of something, right? You know, like the set of real numbers, the set of integer numbers. You can have set of pairs, and so on, right? Set by itself, there is not a lot you can do with it, right? So what we need to do to be able to do something more interesting, like add and multiply, is to give the set some operations. And once we define some operations, then we want some properties for these operations to observe. That these operations cannot be just arbitrary, but they need to have some special structure. And once we do this, we have an instance of an algebra, and a simple instance of that is a vector space. So specifically in vector space, we take some set, and on the set we define scalar multiplication and vector addition. So those are the two basic things you can do to a vector. So vector space is a set, which is a collection of vectors. In every vector, I can multiply with a scalar, and I can add it to another vector. I guess that's what I was already like informally showing with this linear combination, right? And I multiplied every vector by a scalar, and I added vectors together. And for this to actually make sense or be useful for us, some properties need to be true, right? So let's go through them. So the first one is what we were basically like taking for a given, I guess, right? When I said that we just sum two vectors, I assume that the result will also be a vector, right, in the same vector space. But that would not have to be the case in general, right? So this is one of the properties. So this is what we require from vectors to satisfy. If I take two vectors from some vector space, for example Rn, and I sum them together, I get another vector. So for R to n, it's trivial, right? If I have like, for example, R to 5, right? I have just two column vectors of 5 numbers. If I sum them together, I get another column vector of 5 numbers, so this is fine, right? But there can be like some other examples of vector spaces where maybe this would not be that simple to see. So the second property, how this would be called. So what I want is for every two vectors, x and y, I want that x plus y plus x is the same thing. So this has a name. You must have heard that before. Huh? Commutativity, exactly. So that's a special property of addition, right? That there it doesn't matter if I do x plus y or I plus x. And we will see later that in other algebras like matrix multiplication, this will not be true. So the third one also has a name, right? So first, let's just read it. So for all vectors x, y, and z, it doesn't matter if I add first x and y and then add z, or if I first add y and z and then add x, right? So it doesn't matter which way I sum it. I can either first sum the first two and then add the third one, or the last two and add the first one. So this is called, you know what it's called? Associativity, exactly. Maybe I could just write it here, right? This would be commutativity. This would be associativity. Again, like if you are working with something like R2N, which is what we'll be mostly working with, you might think that's stupid, right? That's obvious, right? Because that's what addition on real numbers satisfies. But once we like start thinking about matrices and some other more esoteric structures, then you actually may want to like wonder, oh, is this actually associative? So the fourth thing is that there is an element called 0, or origin of the vector space, which has the special property that whatever I add it to, whatever vector x I add this 0 to, I get back x. So in every vector space, there is an origin, 0 vector, which does nothing on addition. That also will be important later on when we get to like affine spaces and translations. You will see. Just try to remember and trust me that this is not just like theory for the sake of theory. So the fifth property is that for each element we can find an like inverse element or negated element, which has the property that once added we get back the 0. So like as geometrically you could say like every arrow I can like invert. So the remaining ones from 6 to 10, they are about scale when scalars enter the equation. So I should have been actually a little more precise. So vector space is always defined over some field. So in this case, I think we will be just purely considering vector spaces over the reals, right? And what does it mean over the reals? Then the reals are the scalar there. So in this case, so what one's the sixth thing? Yeah, that's the analog of the number 1, right? But for scalar multiplication. So it says if I take whatever vector x and whatever scalar alpha, if I do the scalar product alpha x, then I will again obtain a valid vector. Again, in R2N, trivial, right? Because if I just take column vector and I multiply it by a scalar, that means I'm multiplying every single coordinate in that column. So obviously I'm also getting a valid R2N vector, right? Is that clear? Number 7 is slightly more interesting. So what does it mean? It means if I take two scalars alpha and beta and an arbitrary vector x, then it doesn't matter if I first multiply the scalars together. So here the scalars are just a real number. It's just like floats or doubles if you are like thinking programming. So first multiply the scalars and then do the scalar multiplication of the vector. Or the other way around, first multiply it by beta, scalar multiplication, and then do another scalar multiplication by alpha. So like notice that like if this was like programming, so this function call would be like different type than this function call, right? This would be like multiplying vector by a scalar as opposed to this would be multiplying two scalars. So like if you are thinking computation, you could like immediately notice one thing, and that would be the form on the left is probably more efficient computationally, right? So if you think about it, if I'm doing it the way on the right, that means I have to take every single component of x. So if x is a million-dimensional vector, I have to do million operations, look at million components, and multiply it by beta. And then do the whole thing again. Take again the million-dimensional vector, beta x, and then multiply every single component again by alpha. Right? And this says that I can do it much faster. I can just multiply the alpha and beta first, and multiply every component of the vector by the product of alpha and beta. So number 8 is one form of distributivity. So it's saying that, well, it doesn't matter if I first add alpha and beta and then do the scalar product with x, or do first the scalar product alpha x and then beta x and sum these two together. So that's like one type of distributivity. So I guess number 7 could be like associativity with respect to scale multiplication, if you wanted to name it somehow. And number 8 would be like distributivity with respect to addition of scalars or something like that. Number 9, yeah, it gets annoying because there's lots of these properties, but each of them is like really important. Take it away and you will not get a vector space. So number 9 is the analog, except that here I'm adding 2 vectors. So actually maybe I should have mentioned that. I don't know if you can see it clearly. So these x and y are in bold font, and bold font usually denotes vectors. Sometimes when I'm like writing it, but just sometimes I like write little arrows for vectors x, y, and then no arrow for scalars, just to like differentiate, but to like remind you what is a vector and what is a scalar. And finally, the final property that the unit 1 in the real numbers, that does nothing if you multiply any vector with it. So that's basically just like the 0, but in terms of scalar multiplication. So when I was like taking linear algebra classes, I was like, this was like really boring. I like didn't understand why to worry about that. It only started to make sense to me later when I was like worrying about some like more exotic algebras like quaternions and beyond, where these things like associativity and commutativity are not for granted and sometimes actually are not true. Nevertheless, for now, we can basically take, or did you have, I should have asked if you had any questions on. So this is a definition of a vector space in general. We will be mostly working with the vector space R to N, where all these properties are trivially true. But I just wanted you to know that there are more general vector spaces. And actually, we will have some example of more interesting vector spaces, like the vector space of functions, for example. That's sort of interesting. So we will use it. So I was saying mostly we'll be working with the R to N vector space, where the scalar multiplication, vector addition are defined as you would imagine, as I already said many times. And here is just this second sentence is like a more interesting example of a vector space, just to give you an idea that this really this is not just R to N or C to N, where the complex vector space, but you can think of like, so let's say to be specific, I have like interval from 0 to 1, and I can take space of all continuous functions defined on that interval. So I take whatever f is a function from interval 0 to 1, and it's continuous. And I can, so this is some set of functions, right? So this would be one function on this space, this would be like another function on that space, right? So here is another. This would not be a valid function on that space because it's not continuous, right? So this is an example of a function that would not be there. I want just continuous functions. If you did not have good enough continuous is like something from calculus. If you did not have good enough calculus, then just accept the fact that continuous means that it doesn't really break apart. There is a solid mathematical definition of that in calculus, which you probably had. The point here is that I can take the set of all these functions and say, that's my vector space. And if I'm saying that, I need to say what is my scalar multiplication. So my scalar multiplication is just multiplying the function by a scalar, right? So basically take the function value, the function returned me, and I multiply it by the scalar, right? So like if this function I multiplied by 2, I would get some scaled version of that function. So I can totally do that, right? I can also define addition, the plus operation on two functions, so just add the two functions together. That's fine. And it turns out that this satisfies all the properties. I should now go and check all 10 of them if they are really satisfied, but trust me that they are. And this is a vector space of all continuous functions. It doesn't matter if it was on the interval 0 to 1 or minus 50, 50, that doesn't matter. Or it could also be from minus infinity to plus infinity, right? There's one funny thing about this vector space of all continuous functions. There's this infinite dimension, but we haven't defined dimension yet. So just remember that when we get to dimension that there's something funny going on. Make sense? Cool. So I'm just building up a setup so that I eventually get to matrices and give you like a little better explanation of what a matrix is than just like an array of numbers, because there is more to it than just array of numbers. So one of the concepts I will need is the concept of basis. I will not be defining the basis formally because I don't want to bore you anymore. I'll just give you the idea. We'll do the formal definition later on. So the idea is that if I have some vector in vector space, I can write it as a linear combination. Remember, linear combination is that what I started with. They just take a bunch of vectors, multiply each of them by a scalar, and sum it together, right? So any element of actually any vector space, but here let's just work with R to n, can be written as a linear combination of basis vectors. That's how basis is defined, almost. So here is it's probably very clear from an example. So if I take some vector from R2, so it's a column of two numbers x and y, then I can write it as a linear combination of these two vectors, vector 1, 0 and 0, 1. And the first one I multiply by scalar x, and the second one I multiply by scalar y. So this is a linear combination. These two guys are called basis vectors. In this case, that's the simplest possible basis you can think about. That's the standard basis or the default basis. These vectors are usually denoted as E1 would be the first one, then E2 is the second one. If you were in higher dimensional space, then I could have then I would just have more zeros down there. So let me actually write it. So if I was in R3, then I would have E1 would be 1, 0, 0, E2 would be 0, 1, 0, and E3 would be 0, 0, 1. You can probably imagine what it would be 4D and so on, right? So again, this might again look stupid to you, right? Because I haven't really done much here. All I have done is I said that there are some two special vectors such that any vector there I can describe as a linear combination of them. And this makes these two vectors special, that I call them a basis. If you think about it, that's exactly what I was doing. So that's essentially a formalization of what I was doing in the Cartesian coordinates, right? When I was like drawing some vector, as to say, look, here is a vector v, and look, there are some coordinates, right? And I like did this, right? I just said there is some vx thing, and here is some v sub y thing, right? And there's like my x is x and y. So that's exactly the same idea captured with the concept of basis. Because my coordinate axis, so instead of calling this x, I can call this E1. Instead of calling this y, I can call this E2. Right? It's because in like 100 dimensions I would run out of letters, so I better give it numbers. And then this Vx or V1 or whatever you want to call it is this scalar that multiplies the first basis vector, and then the Vy or V2 or whatever you want to call it is the other scalar which multiplies the second basis vector. And if I do this, I get back my vector v. What is interesting about this is that this is not the only basis of my R2 space. There's many other pairs of vectors which give me also a basis, right? For example, let's say I took 1, 1, and 1 and minus 1. These two vectors also define a basis, right? Because whenever you give me a vector in R2, I can find coefficients x and y such that for whatever vector you gave me, I can find these x and y's. We could try. Do you trust me on that, or shall I do an example? Maybe let's do an example just to give you a better idea. Maybe here. Maybe I can just keep it here. So let's say I take vector 3 and minus 5, right? So in this basis, you can immediately tell me what is the x and y, right? X is 3 and y is minus 5, right? That's stupid. What about in this basis? Well, in this basis, it's not as simple anymore, right? What I need to do is I need to like essentially write down the system of equations. So here A is 3 and B is 5, right? So I have that x plus y needs to be 3 and x minus y needs to be 5. So that gives me... Actually, I wanted to do... Oh, sorry, it was supposed to be minus 5. I said minus 5, just to make the example a little more interesting. So that gives me a 2x is minus 2, so x is minus 1. Which means that y is then 4, right? So let's see if that works. So if I do minus 1 times the first one, 1, 1, plus 4 times the second one, 1 minus 1, what do I get? I get minus 1 plus 4, that's 3, and minus 1 minus 4 is minus 5. So I really get back this. Hey, are you able to follow it on this? So the point is that there is not just this one standard basis, but there is many other bases. But the standard one is really the simplest basis you can come up with. Okay. So that was quick intro to basis of a vector space. And we are slowly getting there. So one more concept. Yeah, like usually the first lectures are like full of new concepts. One of the new concepts you have to swallow is the concept of linear transformation. So the idea is of what is a linear transformation? Linear transformation is a mapping from one vector space to another vector space, which has some special properties. So again, like bunch of definitions. Here it's actually not as painful as like 10 points. Here it's much easier. So if I wanted to write it like symbolically, I could say that T is a function that maps from V1 to V2, where V1 and V2 they are vector spaces, right? For example, I could want like mapping from R2 to R, right? Or from R2 to R5, whatever. By the way, just R, just the set of real numbers, you can also look at it as a vector space, right? It doesn't have to be R2 or R3. It's slightly boring because it's just vectors just with one component, but it's also perfectly valid vector space because it satisfies all my 10 requirements on a vector space. So, what is the definition of a linear transformation then? So so we will say that this transformation, I could have like any transformation from one vector space to another vector space, right? But not all of them are linear. They are linear only if they satisfy this property. So for any scalar alpha, any scalar beta, and for any vector v and any vector w, and these v and w are from the first vector space, the application of t on this linear combination of vectors v and w has to be exactly the same as first applying the transformation on V alone and multiplying by alpha, and multiplying the T alone on W, and multiplying by beta, and then summing together. So this is just a linear combination on the mapping of V and W. So the T of V is where the vector V maps to. T of W is where the vector W maps to. And this is saying that it doesn't matter if I take the linear combination first, in the first vector space V1, and then do the transformation, or if I first do the transformations, so go to the second vector space V2, and then take the linear combination there. So again, like you can see the beauty of algebra, because it's telling you some sort of symmetry, right? You can hopefully see it, if not from this, then like from my rhetorics about it. So think about it. It really doesn't matter if you like first do the linear combination and then the transformation, or first the transformation and then the linear combination. Either way, you get to the same result. So this is just the same thing written again, just so you really remember what is a linear transformation. Have you heard the concept before, linear transformation? I guess the best way to understand some concepts in mathematics is to look at examples. So we'll look at a few examples of linear transformations. So like really simple examples. So scaling a vector by a scalar, right? That's what I call like scalar multiplication. But you can look at it as mapping from, so this in this case it would be mapping from vector space V to vector space V, right? That's fine, because I never said that V1 has to be different from V2, right? It's actually quite common to have linear transformation between the same vector space. So this is the case, and then scaling a vector by a scalar is an example of a linear transformation. And you could verify this property, but again, it's really simple. it's immediately obvious. Another example, a little more interesting now. So if we are in R2 and we reflect the vector about the x-axis, so that means if I have on the input vector xy, then on the output I have vector x minus y. By the way, this is if you're like familiar with like programming, MATLAB or whatever is your favorite programming language, you can think about transformations as functions, right? They take something on the input, they produce something on the output. Right? And the linear transformations are a especially simple class of transformations which obey the property of linearity, which I was talking about before. So reflection is an example of that. So let me give you a geometric picture of the reflection. So if I have a vector V, this is my vector V, what would be the reflection of V? Think about it for a second, and then I will draw it. It's easier to draw than to say. So this would be my TV, right? This would be the reflection. I keep the x coordinate and I flip the y coordinate. And again, you can verify very easily that this property is true. So doesn't matter if I do a linear combination first and then reflect it, or first reflect it and then do a linear combination. It could be like doing a proof, but I think it would be wasting your time. A third example is apply a dot product to a vector. So that means, so here let's be a little bit careful. Here the W is fixed. The function only operates on V, so V is my parameter to the function. And what the function returns me is the dot product of V with W, where W is fixed. So what is the type of this function T here? So it takes a vector from R to N and returns what? Slightly trick question. Huh? Scalar, yeah. So it's a function that goes from R to N to R. You could also like think of R as like R to 1, right? Like one-dimensional real vector space. That's totally fine. So that's another example of linear transformation. So how the concept of linear transformation ties to a basis very elegantly. because of the linearity property, that's the only property that defines a linear transformation. So let's see. I said before that if I take an arbitrary vector b, I can express it as a linear combination of basis vectors, right? So this is my linear combination of basis vectors. In R2, I have just E1 and E2. For any v, I can find the x and y such that this equation is true, right? And now if I have some linear transformation on R2, that means TV, then by linearity, because v is just the sum, v is x E1 plus y E2, and by the linearity of linear transformation, I can write that this is the same as applying the linear transformation only to E1 and E2 and then taking the linear combination with x and y. Is that clear, or shall I write the one step there? The one step that's sort of like implicitly missing here is that this is equal to t of x E1 plus y E2. I will even give you the arrows here to be like super clear. And then by the property of linearity, this is equal to this. Very, very simple. But what is it saying? It is saying that the action of a linear transformation is entirely captured by its action on basis vectors. The rest is just taking linear combinations. In other words, if I have a linear transformation and I want to understand what it's doing, all I need to know is to find out what the linear transformation does on the basis vectors, right? Once I know this TE1 and TE2, then I can compute the action of the linear transformation on arbitrary vertex V, right? Because for arbitrary V, I can find this x and y. And if I already know the TE1 and TE2, well, then I just put it together through I do a linear combination, and I have my TV. Right? So all I need to know about linear transformation is where it maps the basis vectors for an arbitrary basis, right? Because I didn't have to take the standard basis. Like normally people do take the standard basis, but sometimes there are reasons why you need to take some other basis. And finally we got to a matrix. Here is the note about finite dimension vector spaces. But all these R2n are finite dimension. Like the space R2n has dimension n, right? The special case R21 has dimension 1. So that there it's fine. And then the matrix can be interpreted. So if you know that if I have a matrix that's just like some array of numbers, right? A11, A12 to A1n, and here would be A22. Oh, sorry, A21, A22, A2n, and here would be AM1, AM2 to A. It's really difficult to write here. MN. But the linear algebra way to explain what a matrix is, that the matrix, the individual columns of a matrix are the transformations of the standard basis vectors by some linear transformation. So this is basically what I was saying on the previous slide. So that I need to just find what the action of the linear, or what the vector that E12 maps through transformation T is, and what the vector that E2 maps to through transformation T is. That's in Rn, it's some column vector, so some stack of numbers, right? And I just can put them all together in individual columns, and I have a matrix. So let's try to go through an example. Maybe it will be clearer from an example. So let's say I have a mapping from R2 to R2, which maps vector x and y to this. So the first component is 5x plus 6y, and the second is 2x minus 3y, right? So let's go through all I said before in general on this specific example. So first of all, I have the standard basis here, right? So this vector x and y has coordinates x and y with respect to the standard basis. So all I need to look for is what is where the vector e1 and e2 map by f, right? So let's see, so where e1 maps to. So that means x is 1 and y is 0. So that maps to 5 and 2, right? X is 1, y is 0. So I get this. Second one, e2, so this is my e1, this is my e2. E2, that means that x is 0, so here I substitute 0, and y is 1, so I get 6 and minus 3, and I write it here. So instead of writing it this way, like x times the vector 5, 2, and y times vector 6, minus 3, I can just define a matrix which stacks these column vectors, 5, 2, and 6, and minus 3. That's my matrix. And I can say that this function f then is a matrix multiplication of a vector xy times the matrix. It really means nothing but this. Right? Take the first column multiplied by x and add it to the second column multiplied by y. That's also how matrix vector multiplication is defined. Well, let's go to this one. Here is like another example. So here is the example when my linear transformation is a dot product with a fixed vector. So my fixed vector is uv, and my variable vector is xy. So again, if you go through it, I need to look what does the linear transformation do on the basis vectors. I need to end, right? So let's just finish this quickly. So on 1, 0, this gives me just u. On 0, 1, this gives me just v. So I can write it as a matrix vector multiplication where the matrix just has one row, and it's the matrix uv, and my vector is again still xy. So this is another example of how to represent a linear transformation with a matrix. Okay, so I think we got it all. If you have any questions, please shoot. We will continue in this on Friday. Tomorrow you should do some more MATLAB stuff.